my name is Mitch Miller, and in this video I'll be talking about neural evolution and how it relates to video games. Neural evolution is primarily found in the research on AI and games, but it also does include some interesting ways on how it can benefit game design as a whole. First off, a brief outline of what we'll be covering in this video, an overview of neural evolution, some examples of the applications of it, some specific algorithms of neural evolution, the current open challenges within this area, and then a summary of what we discussed. Moving on to the overview, what is neural evolution? Neural evolution is the generation of artificial neural networks through evolutionary algorithms. The motivations behind this concept are the following: the fact that it mimics the brain and its neurons and evolution, the fact that it's a good way to search unsupervised, meaning that you do not need a good input-output pair or good set of input-output pairs to guide your search or your training of your neural network, and the fact that it holds the benefits of evolutionary algorithms, such as being incremental, possibly interactive, and multi-objective. Evolutionary algorithms, I might add, have been studied for a greater deal of time, and the fact that neural evolution is based off this allows it to implore the advances made in that field as well. So why is neural evolution found in games? Well, the answer is twofold. First off, games as a problem to solve are very complex. There's not usually these good input-output pairs for supervised learning, so a search needs to be done on, in this case again, neural networks to see what is the best playing AI. Secondly, AI in games usually need to perform many tasks or adapt to tasks, and an evolutionary algorithm with the ability to support multi-objective goals is very nice. Also, the interactivity of the evolutionary process can be featured as gameplay in the right situations. So a little bit of background on neural evolution. As you can hear in its name, it's the combination of neural networks and evolutionary computation, where the outcome is a neural network that can solve the problem at hand, and the evolutionary computation is the means to which you find a good neural network. So what does this look like? Well, one quick example in video games is Mario. Mario is an example of using neural evolution to train a player to play a certain Mario level. As you can see on the left, there's one of the original neural networks with very few neurons and very few connections, taking input from a simplified map and translating that to controller input. On the right side, you can see a much more developed neural network that's able to traverse the level and dodge enemies and collect coins, and with it comes a neural network that has much larger amount of neurons and connections. So Mario is just one example, but how do we break up the applications of neural evolution in video games? And one way to break this up is into these four categories: state action evaluation, direct action selection, modeling players or opponents, and content generation. State action evaluation is used to evaluate the quality of a state, such as a chessboard or a Go board. The neural network will take this as input and provide some sort of value or heuristic to be used in some other algorithm. For example, Monte Carlo tree search needs a function to calculate the exploitation or exploration during its search, and one way is to leave that function up to neural evolution to develop the best possible AI for the specific game. Direct action selection takes us a step further, going from the input of the game state, whether that be the actual picture on the screen or some sort of human selected variables, and determining the proper action to take at that time. As you can see, this is where Mario falls, where it takes in a human-designed map of inputs and translates it to the controller inputs of Mario. Another large example of this is the Atari games, where neural evolution has been used to create a neural network that translates the pixels of the game directly to controller input. Thirdly, neural evolution can be used to model players or opponents. So instead of the fitness function evaluating the performance of the neural network objectively, it evaluates the performance of the neural network as compared to a specific type of player. You can think of this as trying to evolve a neural network that acts like an aggressive racer or a very defensive strategy in an RTS. Lastly, there's content generation, which is very different from the other three categories. This is where the interactivity of evolution is used as a feature in a game. This can be seen from the original paper of neuroevolution of augmenting topologies in the game Neuro, where the player evolves a bunch of AI bots that fight against one another, adjusting the evaluation of their performance, which thus influences how the next generation of bots is evolved. Following this, there was a game titled Galactic Arms Race, where a player could find new ship weapons that had been evolved from the previous weapons that player had used. As you can see, this allowed for a variety of weapon projectile patterns that the player could search for and find. Another example of this was a website titled PicBreeder, which is an interactive neural evolution of images, which allowed for people to collaborate and create interesting images, as you can see here. Putting this all together, neural evolution in video games allows for the development of good AIs within the video game, good player approximations to possibly test a video game or exhibit more controlled AI behavior, as well as an integration within video games as a feature through the use of content generation. Moving on from this, I want to talk about the categories of neural evolution and dive into a specific algorithm to provide some more insight on how neural evolution works. First off, there are two main ways neural evolution algorithms are categorized: whether they have fixed topology or the topology is evolved, and whether they have a direct encoding or indirect encoding. To provide an example, a fixed topology with a direct encoding could look like this, where you have a neural network whose topology doesn't change, and all the weights and biases of the neural network are encoded directly into, say, a bit string. If the topology needs to be evolved, then a more complicated algorithm is necessary. To highlight this, I'm going to go over the neural evolution of augmenting topologies. This algorithm was made to both support the evolving of the topology of a neural network and its weights. As we mentioned before, one of its main motivations was to complexify a neural network over time, as well as find multiple solutions for the problem at hand. So how does the NEAT algorithm work? First off, it has a much more complex encoding. There are actually two direct encodings, one for the nodes or neurons of a network, and one for the connections. Within these connections and nodes, there are multiple different values that can be evolved. Looking at the graphic, there are node genes and connection genes, and in these lists, the order is maintained. Each parent's list of connections is compared in a specific order so that the offspring's list of connections does not contain any erroneous connections. One other thing in maintaining the list of genes is that during mutation, a node is disabled or a connection is disabled rather than being removed from the list so that the order can be maintained. We see that mutation is also the step to add or remove connections in the form of disabling, as well as editing any parameters such as the connection weights or the neuron's biases. So this is an example of a more complicated neural evolution algorithm where both the neural network's topology and parameters can be evolved. In the case of NEAT, the genes are encoded directly. This can cause problems in large networks as computation times will increase because of the larger lists of genes. So to bring in another example, a modification of NEAT titled HyperNEAT provided an indirect encoding for neural networks. In this case, a small neural network was used to determine the weights of a much larger fixed topology. This allowed HyperNEAT to perform raw pixel game playing, such as the Atari games we saw earlier, where the screen's pixels were used as input to the neural network and the output was the game actions possible. While I only covered a few algorithms, I hope it encapsulates what it means to have a fixed topology or evolving topology neural evolution algorithm or a direct or indirect encoding for the neural evolution algorithm. Additional algorithms of note can be seen here. So now I want to provide you with some of the open challenges in neural evolution. First off, there's what any other algorithm's open challenge is, which is to beat the performance of other record-breaking algorithms. Next, there's combining neural evolution with other learning methods. In the field of neural networks, there are lots of different ways to train the weights on a neural network, such as backpropagation, reinforcement learning, etc. After that, there's using neural evolution to tackle high-dimensional or raw data. This amount of data usually requires a large neural network. And as I mentioned about the NEAT algorithm, a direct encoding of a large network can vastly increase the computational time required to train such a network. This means to process that amount of data, indirect encodings and new algorithms need to be explored. After that, there's general video game playing, where a neural evolution algorithm would be used to try and play many video games, such as the Atari games found on OpenAI's Gym, or other sets of games. And lastly, an open challenge would be to seek the further use of neural evolution within the professional video games industry. It's been shown that neural evolution can be used as a feature within games for content generation, and this can allow for video games to have a larger amount of content for the player to explore. In conclusion, I outlined how neural evolution provides great techniques for unsupervised searches for solutions, how it mimics evolution and the brain's neurons, which should provide a better model of human behavior, and that evolutionary processes allow for varied emergent solutions to be discovered. How does this look in video games? To me, I see neural evolution in video games as a method to model players, which benefits both creating better AIs within the game, as well as better testing of modeling different player personalities, and as a platform for content generation, where a neural evolution algorithm can be placed within a game to create content that both adapts and evolves as the player progresses.